It's evolution. You start with initial MV, how your MV will increase or decrease with time. Well, here is the rule. The rate of change of your MV is simply the force. Okay? You're now proposing another fundamental quantity that might be actually easier and better to deal with than Newton's. Why? Because mv squared is scalar quantity, whereas this is a vector quantity. It's always easier to deal with scalar quantities than vector quantities. So that's fine, but what is its update rule? How are you going to update it? He came up, postulated, he assumed, similar to this assumption, this one, which looks more actually convincing. The change in kinetic energy simply equals the amount of work done by the forces. You apply some work to the system, you get it into the form of energy. Okay? And if you remember in your undergrads, sometimes this equation was much better, clever than Newton. Here is one example. A mass on an inclined plane, right? Under the action of gravity, it starts from rest. And we're interested to determine the velocity by which it will hit the bottom. Okay? You can do it using Newtonian mechanics. Start with the very first principle, F equals ma. So here's ma, and here's the force. It's mg sine theta, the acting force along the incline. So you got the acceleration. From the acceleration, you start to go to kinematics. Integrate the acceleration once to get the velocity, integrate the velocity once to get the position, and then equate your position with the distance traveled, right? To get the final time, you substitute the final time back to the velocity equation to get the velocity, the final velocity, right? Well, it's very doable, of course, and easy, but several steps. Whereas on the other hand, changing kinetic energy equal the work of the force done. Kinetic energy final minus kinetic energy initial equals the work done, which is the acting force, mg, times the distance along the force, d sine theta. It's just this line, because you start from rest, this guy goes away, immediately you get your final, right? So sometimes, or some cases, many problems, this energy-based formulation is much easier, much more clever than Newton. But it's not complete by any means. It's not sufficient by any means. Why? If you go back here, like I said, there is a fundamental difference between Newtonian mechanics and the analytical mechanics. Is that the quantity here, mv and mv squared, are fundamentally different. mv is vector, while mv squared is scalar. Which means if you have an equation for mv, this is a vectorial equation. So in space, in three-dimensional space, this is three equations. It's not a single equation, right? Whereas over there, we have just one single equation. Okay? So this is the thing, is that if you have a particle moving in three-dimensional space, you have 3 degrees of freedom. For these degrees of freedom, you have 3 equations coming from Newton. Over there, you have only one equation of motion. So it's not complete, right? So this was the main problem of this branch. So how to proceed? This was the main problem. Until Nobel came, he's a French scientist, as the name may tell. And actually, he came up with a philosophical principle. Very neat philosophical principle, but still, it's just philosophical thing. How to apply it. But this philosophical thing, actually, which laid down the foundation of everything. Turns out to be the most fundamental principle in dynamics, and he by far outweighs and outperforms the Newtonian mechanics, and this is our main topic during the entire course, which works in our length scale, in the very large scale, in the very small scale, and the Nobel Laureate Richard Fineman, he got his Nobel Prize because he applied this to very small scale and developed the quantum mechanics. So he was giving a lecture after his success, And at the beginning of the lecture, he said one day he was very bored. His high school physics teacher found him that bored. He said, "Richard, come, I'll show you something interesting." So Richard Fineman is now, I'm quoting, he said, "Then he told me about something which I found absolutely fascinating and have since then always found fascinating. Every time the subject comes up, I work on it. In fact, when I began to prepare for this lecture, I found myself making more analysis on the thing. Instead of worrying about the lecture, I got involved in a new problem. This thing is a principle of least action." But we said that nature should be very wise, and things should not be happening haphazard. Should be happening in a very optimum way. Which means what he's proposing is that, remember, all these are assumptions. This is an assumption, this is an assumption. He's assuming something. He is assuming what? That every single motion in this universe is happening such that a certain magic quantity is minimized. Okay? So, well, this seems neat, but what is this quantity? Because if we know it, then we're done. Why? Because we're going to gather, we have about 40 people here. We're going to sit and say, okay, we want to study the trajectory of this guy. Well, everybody going to assume a trajectory. This thing, that thing, this thing, okay? And everybody going to compute this magic quantity along his trajectory, her trajectory. We're going to gather them and see the one with the minimum of that quantity. And this would be the right trajectory, right? So it turns the dynamics problem into an optimization problem. We're optimizing some magic quantity. So there is controversy whether Nobel came up with that magic quantity or not. I believe that it's Euler. And like I said, this is the principle of least action. Turns out that this magic quantity is the vis viva, the kinetic energy. So the integral of the kinetic energy along your trajectory is minimum. Okay? So every single motion in that universe, if I just let this guy fall down, if a spacecraft is orbiting, if just one of the planets is orbiting, whatever, all these behave and move such that this integral is minimized. In the very large scale, in the very small scale, and in our length scale. So Euler and Lagrange, they formulated such a problem. They said, okay, you know what, the motion is such that this integral is minimized, subject to some constraint that the energy is conserved. And actually, it seems that this is a hard problem. If you give me a function of some variables and ask me to get the minimum, I'll just differentiate and equate to 0, right? Partial x equals 0, get an equation, solve for x for optimum. That's right, but this is not an easy function. It's an integral. So how are you gonna get the minimum of an integral? This is not very straightforward, and yes, it wasn't. It's harder, and it necessitated a new type of mathematics, which Lagrange has developed. He developed a new calculus called calculus of variations, which is one of the things that we're going to consider in this course. And this is why actually Hamilton, the big name, the next big name in chronological order in dynamics, he used to call Lagrange as Shakespeare of mathematics. Because think about it, you encounter a hard problem such that the current mathematics is not sufficient to solve it. So he said, okay, well, let's develop a new calculus for it. Turns out to be very, very useful outside the branch of dynamics. We use it in many different other things. Actually, it's very well matured discipline now in every single department of mathematics, almost in the country. They teach calculus of variations course. So it has almost nothing to do with dynamics. If you apply it to dynamics, you'll get the principle of least action, but it is applicable to a variety of problems. So I have to say that also Euler contributed here. He developed very similar set of equations to F equals ma, to the rotation of a rigid body. simply, instead of linear momentum, he replaced it with angular momentum, because we're talking about rotation now. And the rate of change of angular momentum would be simply the moment, not the force. Which you can get his equation from this equation by just do a cross product for the whole equation with the position vector arc. So it's not a new thing, but it's very well established now. We use it automatically without deriving it every time from Newton's equation. And he also introduced the Euler angles, which we're going to discuss in this course. Okay, for this branch to proceed, like I said, Hamilton came and he developed the exact statement of the principle of least action. Because one of the conceptions, one of the misconceptions about this branch, the energy-based methods, Lagrangian mechanics, or whatever, people, few people think that it is only concerned with simple problems where energy is conserved. This is wrong. No, of course not. Using this branch, we will be able to solve the most complicated problems in dynamics whatsoever in a much easier way than Newton. So actually, Hamilton formulated this problem or generalized this problem for cases where energy is not conserved. He said, you know what? Actually, the integrand that should be minimized is not only the kinetic energy, it's the difference between kinetic energy and potential energy. And I see it like this, you know, it seems that things in nature are lazy. They don't want to increase their kinetic energy, and they want to keep their potential energy. Potential energy is an energy due to position. If I'm in a good position, I don't want to leave it. Okay? So we want to minimize this guy over the trajectory. This is the right trajectory. That minimizes this quantity. And actually he said, you know what? It's not necessarily E minimum. When you have a function and its first derivative is 0, you differentiate and set it to 0, right? So the slope is 0. First derivative is 0. This point might be minimum, maximum, or nothing. Saddle point, right? So in the three cases, we call this point a stationary point. Stationary point meaning the first derivative is 0. So he's saying actually this integrand might not be minimum, but we're sure that it's stationary. Its first derivative is 0. In most of the cases, it's minimum, but sometimes it's not. Particularly if the time of the excursion is small, it's gonna be minimum. And actually, we don't call it the first derivative of this guy. If you have a function, you want to get its maximum or minimum, you differentiate it, get the first derivative, and equate it to 0, right? For an integral, we don't call it first derivative. We call it first variation. And this is why it's called the variational mechanics. Okay? So the principle of least action is that the first variation of the action integral is 0. Okay? And then he developed something called canonical equations that make your every dynamical system with some properties look like an incompressible flow with very good special structure that we can exploit. Also, Jacobi did the same and worked on these canonical equations a bit more. And what else? Yeah, and developed something called constants of motion. It was known before him, but he made constructive techniques to derive constants of motion. If you have several variables, x and theta, y, blah, blah, describing your system, sometimes it's good to identify constants of motion, something like, well, if x dot squared theta sine theta, for example, is constant along the motion, this is a good piece of information because I will be able to know the initial conditions for my theta and the x dot, and this multiplication will have this value constant over the entire motion. So he gave us some constructive ways to know these constants of motion, because these constants of motion are typically associated with some momenta about some direction. So it's good to know somebody tells you that, oh, you know, your system has a conserved momentum about this direction. You didn't know before. So he gave some techniques to know that, whereas in Newton, there's no way to know that by construction. You have to know it from your knowledge from the problem. Okay, we're summarizing. We have two main branches of dynamics. Like I said, the Victorian Newton mechanics versus analytical variational mechanics. The two main quantities here is the momentum and force. The rate of change of momentum is the force. This is Newtonian mechanics. Both quantities are vectors, so we're going to be dealing with vectors all of the time, and this is why it's called Victorian mechanics. Of course, dealing with vectors is a bit hard, and we need to be cautious when dealing with vectors. Over there, the basic quantities that we're going to be dealing with is the kinetic energy and work. And both are scalar quantities. Okay? Like I said, if you're dealing with vectors, then you have to pay too much attention. We're going to see it in problems, too much attention to the coordinate system. Why? Because if you have a vector represented in an inertial frame and differentiated, is completely different if you have a vector represented in another frame and you want to differentiate it. Whereas here, actually we don't care. Formulate your problem the way you like, whether it's an inertial frame, non-inertial frame, we don't care. We're going to just turn the crank. Actually, this algorithm is very programmable. Give me the hardest problem in dynamics ever. I can make any professor in the world. I give him or her a tricky problem in dynamics, and it's very easy to mess up with it. It's a very hard problem in dynamics, but I'm going to force him or her to use Newtonian mechanics. Okay? It's very easy to get perplexed. Whereas this guy, I don't care. Actually, the irony is, we typically study this in our undergraduate, and we typically study this in our graduate, whereas it's typically easier to solve problem using Lagrangian mechanics than Newtonian mechanics. So I'm working in my research with flapping wing microwave vehicle. So we have a body, 6 degrees of freedom, and each wing has about 3 degrees of freedom with respect to the body. We have 2 wings. It's very messy to derive even the equations of motion for our experimental setup, whereas we have about 2 degrees of freedom or 3 degrees of freedom. It's very tricky. Whereas here, we really don't care. It's just, give me kinetic energy, give me your work, because kinetic energy is very easy, 1/2 mv squared. Give me your velocity, 1/2 mv squared, we're almost done. You're gonna see this. So this is the privilege that we're gonna have. Like I said, Newtonian mechanics fails at very large and very small scales, whereas this guy nuts. The principle itself, the principle of least action is that every motion is such that the action integral is stationary. This principle works